I'm going to cover 3 sections today on elementary number theory and methods of proof. Direct proof and counterexample introduction. Both discovery and proof are integral parts of problem solving. When you think you have discovered that a certain statement is true, try to figure out why it is true. If you succeed, you will know that your discovery is genuine. Even if you fail, the process of trying will give you insight into the nature of the problem and may lead you to discover that the statement is false. For complex problems, the interplay between discovery and proof is not reserved to the end of the problem-solving process, but rather is an important part of each step. Now, some assumptions about the numbers and theory and assumptions that are going to be used throughout this chapter. We assume that you have a familiarity with the laws of basic algebra. We also use the 3 properties of equality, shown here. Principle of substitution. If for all objects A and B, if A equals B, then we may substitute B wherever we have A. In addition, there is no integer between 0 and 1, and the set of all integers is closed under addition, subtraction, and multiplication. This means that sums, differences, and products of integers are integers. Even, odd, prime, and composite numbers. An integer definition. An integer is even if and only if n equals twice some integer. An integer is odd if and only if n equals twice some integer plus 1. Symbolically, for any integer n is even if n equals 2k for some integer k. N is odd if and only if n equals 2k plus 1 for some integer k. So, is 0 even? Yes, because 2 times 0 is 0. So it's 2 times some integer. Is 301 minus 301 odd? Yeah. Minus 151 times 2 plus 1 equals 301. If A and B are integers, is 6a squared b even? Now, so you're thinking on this. What's the definition of even? Just to add it up there. If it's even, then the number equals 2k for some integer k. If A and B are integers, and integers are closed on multiplication, 6a squared b equals 2 times 3a squared b. 3a squared b equals is an integer because it's closed on integers. Multiplication is closed on integers, so you can say m equals 3a squared plus 3a squared b. M is an integer, so 2m 6a squared b equals 2m for some integer m, which is the definition of even. It is even. Yeah. If A and B are integers, is 10a plus 8b plus 1 odd? Yes. Yes, it is. Yeah. Is every integer either even or odd? Yeah, pretty much. Yes, for all of the above, for those reasons. And the last one, every integer is either even or odd. However, the reason for this fact is not immediately apparent. It can be deduced by using the method of proof by contradiction. It is also a consequence of the quotient remainder theorem, which we will get to later. An integer n is prime if and only if n is greater than 1, and for all positive integers r and s, if n equals rs, then either r or s equals n. An integer is composite if and only if n is greater than 1, and n equals rs for some integer r and s, with r being between 1 and n, and s being between 1 and n. And symbolically it gives it here. Is 1 prime? No, because it has to be greater than 1. Is every integer greater than 1 either prime or composite? Yes. What are the first six prime numbers? Hmm? 2? Okay, that's 1. Prime numbers. So it's 3, 5, 7, okay. One more. There you go. And the first 6 composite numbers? Missed one. Yeah. And there you go. There you go. And it goes into explanations as to each one. And let's see here. It gives the C and D twice there. Proving existential statements. According to the definition, a statement in the form, there exists an element in D such that Q of X is true, is true if and only if Q of X is true for at least one X in D. One way to prove this is to find an X in D that makes Q of X true. Another way is to give a set of directions for finding such an X, and both of these methods are called constructive proofs of existence. The logical principle underlying such a proof is called existential generalization. It says that if you know a certain property is true for a particular object, then you may conclude that there exists an object for which the property is true. There's kind of a obvious common sense thing there. Prove an even integer n can be written in 2 ways as a sum. Prove there exists an integer n such that that can be written in 2 ways as a sum of 2 prime numbers. Suppose that r and s are integers. Prove there exists an integer k such that 22r plus 18s equals 2k. So first let n equal 10. 10 equals 5 plus 5 and 3 plus 7. And 3, 5, and 7 are all prime numbers. Thus, there exists an even integer, namely 10, that can be written in 2 ways as a sum of 2 prime numbers. For b, let k equal 11r plus 9s. Then k is an integer because it is a sum of products of integers. And by substitution in the law of distributive law of algebra, 2k equals 22r plus 18s. Thus, an integer k, so there is an integer k named such that 22r plus 18s equals 2k. A non-constructive proof of existence involves showing that either A, that the existence of a value of x that makes q of x true is guaranteed by an axiom or a previously proved theorem, or B, that the assumption that there is no such x leads to a contradiction. Now, the disadvantage of a non-constructive proof is that it may give virtually no clue about where or how x may be found. The widespread use of digital computers in recent years has led to some dissatisfaction with this aspect of non-constructive proofs and to increased efforts to produce constructive proofs containing directions for computer calculation of the quantity in question. Disproving universal statements by counterexample. To disprove a statement of the form for all of x in D, if p of x then q of x, find a value of x in D for which the hypothesis p of x is true and the conclusion q of x is false. Such an x is called a counterexample. Disprove the following statement by finding a counterexample. For all real numbers a and b, if a squared equals b squared, then a equals b. What's a counterexample? A and b equal what? No, because 3 squared plus and 3 squared and 4 squared are not equal. The squares have to be equal. Yeah, but a and b are not equal. Two and minus two? Yeah, it's not positive integers, it's all real numbers. Yeah. Yeah. So to disprove the statement, you need to find a real number, real numbers a and b, such that the hypothesis a squared equals b squared is true, and the conclusion a equals b is false. The fact that both positive and negative integers have positive squares helps in the search. And we came up with 2 and negative 2. You only need to find one such pair to give a counterexample. So, gives it out in symbolic form here. Proving universal statements. Use the method of exhaustion to prove the following statement. For all n in all integers n, if n is even, and n is between 4 and 26 inclusive, then n can be written as the sum of two prime numbers. Well, go through all the numbers between 2 and 26, or 4 and 26, and give examples. That is proving by exhaustion the statement is true. You exhaust all the possibilities. Now, the most powerful method, technique for proving a universal statement is one that works regardless of the size of the domain over which the statement is quantified. It is based on a logical principle, sometimes called universal generalization. Descriptive name being more like generalizing from the generic particular. So that means to show that every element of a set satisfies a certain property. Suppose X is a particular but arbitrarily chosen element of the set, and show that X satisfies the property. At some time, you may have been shown a mathematical trick like the following. You ask a person to pick any number, add 5, multiply by 4, subtract 6, divide by 2, subtract twice the original number. Then you astound the person by announcing that their final result was 7. You can show that this is the case by imagining an empty box contains whatever number the person picked. Then go through the various steps and show that by the end of the calculations, the empty box was subtracted out of the answer and leaving 7 behind. So those are the steps that go through it, and regardless of what is in X, it gets subtracted out in the 5th step, leaving only the 7 behind. Come on. So you can generalize from the generic particular to conclude that if you follow the steps, you will always get 7, regardless of the initial value you put in place of X. When the method of generalizing from the generic particular is applied to a property of the form if P of X then Q of X, the result is the method of direct proof. And that is step 1, express the statement to be proved in the form of, for every X in D, if P of X, then Q of X. Start the proof by supposing X is a particular but arbitrarily chosen element of D, for which the hypothesis P of X is true. Abbreviated, suppose X is an element of D and P of X is true. Show that the conclusion Q of X is true by using definitions, previously established results, and the rules for logical inference. So prove that the sum of 2 even integers is even. Well, suppose you have 2 integers, even integers, m and n. M, because it's even, is 2r, where r is an integer. N equals 2s, where s is an integer. M plus n equals 2r plus 2s, which equals 2r plus s. And suppose t equals r plus s. T is an integer because it's a sum of 2 integers. So m plus n equals 2t. And since t is an integer, m plus n equals 2 times some integer. Therefore, m plus n is even. Does that make sense? Yeah? Yeah. So, and then they go through it here. Oops. When they go through it here, you cannot possibly check all the pairs of even numbers, so you can not for sure know for sure that the statement is true in general by checking the truth in these particular instances. Many properties hold for a large number of examples and yet fail to be true in general. To prove this statement in general, you need to show that no matter what even integers are given, their sum is even. So it goes through the process that I went through real quick. Now suppose the statement to be proved is more complicated than this. What method can you use to derive a proof? You can begin by expressing the statement formally. This statement is universally quantified over an infinite domain. Thus, to prove it in general, you need to show that no matter what two integers you might be given, if both of them are even, their sum will also be even. Next, ask yourself, how should I start the proof? Starting point. Suppose m and n are particular but arbitrarily chosen integers that are even. Then ask yourself, what conclusion do I need to show? M plus n is even. Since both involve the term even integer, you must use the definition of this term, and thus you must know what it means for an integer to be even. It follows from the definition that since m and n are even, each equals twice some integer. One of the basic laws of logic, called existential instantiation, says, in effect, that if you know something exists, you can give it a name. However, you cannot use the same name to refer to two different things, both of which are currently under discussion. It's kind of like using a variable in a computer program. You can only use it for what you're using it for. You can't use it for the same variable name for two different things. Not in the same scope, at least. So if the existence of a certain kind of object is assumed or has been deduced, then it can be given a name, as long as that name is not currently being used to refer to something else in the same discussion. Which leads us to theorem 411. The sum of any two even integers is even. Getting proofs started. All right. Believe it or not, once you understand the idea of generalizing from the generic particular and the method of direct proof, you can write the beginnings of proofs even for theorems you do not understand. The reason is that the starting point and what is to be shown in a proof depend only on the linguistic form of the statement to be proved, not the content of the statement. Write the first sentence of a proof and the last sentence of a proof for the following statement. Every complete bipartite graph is connected. It is helpful to rewrite the statement formally using a quantifier and a variable. For every graph G, if G is complete bipartite, then G is connected. You got the domain, the hypothesis, and a conclusion. And the first sentence or starting point of the proof supposes the existence of an object in the domain that satisfies the hypothesis of the if-then part of the statement. The conclusion to be shown is just the conclusion of the if-then part of the statement. So the starting point, suppose G is a graph such that G is complete bipartite. Conclusion to be shown, G is connected. Thus, the proof has the following shape. Suppose G is a graph such that G is complete bipartite, yada, yada, yada. Therefore, G is connected. Fill in the blanks in the proof of the following theorem. For all integers R and S, if R is even and S is odd, then 3r plus 2s is even. Suppose that r and s are any integers such that r is even and s is odd. By the definition of odd and even, r equals 2m and s equals 2n plus 1 for some integers m and n. Then by substitution, 3r plus 2s equals 3 times 2m plus 2 times 2n plus 1. Multiplying out equals 6m plus 4n plus 2, which equals 2 times 3m plus 2n plus 1. And you can let t equal 3m plus 2n plus 1. And t is an integer because m, n, 3, 2, and 1 are integers, and because integers are closed on multiplication and addition. Hence, where 3r plus 2s equals 2t, where t is an integer, and so by the definition of even, 3r plus 2s is even. There you go. And that's it for that slide deck. And we'll move on to section 2. Are you going to behave? You're not going to behave. Okay. All right. Direct proof and counterexample 2. Some writing advice. Directions for writing proofs of universal statements. Over the years, the following rules of style have become fairly standard for writing final versions of proofs. Copy the statement of the theorem to be proved on your paper. Makes it available for reference to anyone reading the proof. Clearly mark the beginning of your proof with a word proof. Nothing that says start like start. Clearly mark it. Make your proof self-contained. This means that you should explain the meaning of each variable used in your proof in the body of the proof. Thus, you will begin proofs by introducing initial variables and stating what kind of objects they are. This would be similar to declaring variables and their data types at the beginning of a computer program. So you know what's what and likely how it's going to be used. At a later point in your proof, you may introduce a new variable to represent a quantity that is known at that point to exist. For example, if you have assumed that a particular integer n is even, then you know that n equals 2 times some integer. And you can give this integer a name so that you can work with it concretely later in the proof. Number 4, write your proof in complete grammatically correct sentences. This does not mean that you should avoid using symbols and shorthand abbreviations, just that you should incorporate them into sentences. So, the proof of theorem 411 contains the sentence, let m plus n equal 2r plus 2s. The equal signs, the first one reads as equals, and each subsequent equal sign as which equals. Keep your reader informed about the status of each statement in your proof. Your reader should never be in doubt about whether something in your proof has been assumed or established or is still to be deduced. So use words to indicate what the status is of each statement. This is especially important if you introduce a variable and rephrasing what you need to show. Give a reason for each assertion in your proof. Each assertion in a proof should come directly from the hypothesis of the theorem or follow from the definition of one of the terms in the theorem, or be a result obtained earlier in the proof, or be a mathematical result that has previously been established or is agreed to be assumed. Indicate the reason for each step of your proof using phrases such as by hypothesis, by definition of, by theorem, that sort of thing. Include all the nice little words and phrases that make logic of your arguments clear. Indicate how each sentence is related to the previous one. Does it follow from the previous sentence or from a combination of the previous sentence and earlier ones? So use because or since and state the reason why it follows, or write then and or thus or so or therefore. It follows that, and include the reason at the end of the sentence. If a sentence expresses a new thought or fact that does not follow as an immediate consequence of the preceding statement, but is needed for a later part of the proof, introduce it by writing, observe that, or note that, or recall that. Sometimes in a proof it is desirable to define a new variable in terms of previous variables. In such a case, introduce the new variable with the word let. Display equations and inequalities. The convention is to display equations and inequalities on separate lines to increase readability, both for other people and ourselves. It makes checking for your work for accuracy easier. Variations among proofs. It is rare that two proofs of a given statement written by two different people are identical. I say it never happens. I don't believe it ever happens. Even the basic mathematical steps are the same. Two people will use different notation or may give different amounts of explanation for their steps, or may choose different words to link the steps together. It's kind of like writing a program. A program of any length is going to be different from your neighbor's. Everybody has their own programming style, how they name variables, how they use white space, how they write their comments, that sort of thing. Your proof writing style and your programming style is like a fingerprint. It is unique to you. I once had a pair of twins, joined at the hip all the time, turned in totally different work, because even though they were very as close as two people can be, genetically identical, they wrote different programs. They wrote things differently. But how about some common mistakes? First one, arguing from examples. Looking at examples is a good practice, a helpful practice to engage in, and is encouraged by good mathematics teachers. However, it is a mistake to think a general statement can be proved by showing it to be true for just some individual cases. That is called anecdotal evidence, and it is not a valid method of proof. Consider the following proof that the sum of any two even integers is even. So this is true because if m equals 14 and n equals 6, which are both even, then m plus n is 20, which is also even. When we discussed valid arguments, we pointed out that an argument may be invalid and yet be true, have a true conclusion. So, not necessarily true. In the same way, an argument from examples may be mistakenly used to prove a true statement. In the previous example, it is not sufficient to show the conclusion. You must give an argument to show that the conclusion is true for any arbitrarily chosen even integers m and n. Using the same letter to mean two different things. So, suppose m and n are any two odd integers. Then by definition of odd, m equals 2k plus 1 and n equals 2k plus 1, where k is an integer. You might think of a variable in a mathematical proof as similar to a global variable in a computer program. Once it is introduced, it has the same meaning throughout the program. Its scope extends to the end. In this example, using the symbol k in the expressions for both m and n makes k a global variable. As a result, both m and n are equal to 2k plus 1, and thus are equal to each other. The proof then only shows that the sum of two identical odd integers is even, not that the sum of two arbitrarily chosen odd integers is even. Another mistake, jumping to a conclusion. This means to allege the truth of something without giving an adequate reason. Consider, suppose m and n are any even integers. By definition of even, m equals 2r and n equals 2s. For some integers r and s. Then m plus n equals 2r plus 2s, so m plus n is even. Skipped a few steps. Didn't show convincing arguments that the result is in fact true. Assuming what is to be proved. To assume what is to be proved is a variation of jumping to a conclusion. Consider the following. Suppose m and n are any odd integers. When any odd integers are multiplied, their product is odd. Hence, m times n is odd. Kind of circular logic there. It doesn't show anything. It just assumes what you're trying to prove is true and says, here, it's true. Our theorem is true. Confusion between what is known and what is to be shown. A more subtle way to jump to a conclusion occurs when the conclusion is restated using a variable. In this example, suppose m and n are any two odd integers. We must show that m times n is odd. This means that there exists an integer s such that m times n equals 2s plus 1. But also by definition of odd, there exists integers a and b such that m equals 2a plus 1 and n equals 2b plus 1. Then m times n equals 2a plus 1 times 2b plus 1 equals 2s plus 1. So since s is an integer and m and n is odd by definition of odd. The author restated the conclusion to be shown and the author wrote, there exists an integer s such that mn equals 2s plus 1. But we only know that the integer s exists if we know that mn is odd, which is what the author is trying to show. Thus, in the sentence starting with the word then, the author jumped to an unjustified conclusion. This mistake might have been avoided if the author had written, this means we must show that there exists an integer s such that mn equals 2s plus 1. An even better way to avoid this kind of error is not to introduce a variable into a proof unless it is either part of the hypothesis or deducible from it. Use of any when the correct word is some. There are some situations in which the words any and some can be used interchangeably. In most situations, however, the words any and some are not interchangeable. Here's a proof of that the square of any odd integer is odd, which uses any when the correct word is some. Suppose suppose m is a particular but arbitrarily chosen odd integer. By definition of odd, m equals 2a plus 1 for any integer a. Doesn't work quite right for any integer. It's only for some integer. There exists an integer a such that m equals 2a plus 1 by the definition of odd. Misuse of the word if. Another common error is not serious in itself, but it reflects imprecise thinking. This error involves using the word if when the word because is really meant. Consider the following proof fragment. Suppose p is a prime number. If p is prime, then p cannot be written as a product of two smaller positive integers. Well, this if p is prime puts p being prime in doubt, but in the previous sentence, you're stating p is in fact a prime number. So, because p is prime, then p cannot be written as a product of two smaller positive integers. The use of the word if is inappropriate. Correct version of the fragment. Suppose p is a prime number. Because p is prime, p cannot be written as the product of two smaller positive integers. Prove that the difference of any odd integer and any even integer is odd. Use only the definitions of odd and even and the assumptions listed below, which we discussed earlier. Not any other properties of odd and even integers. Follow the directions in this section. All right. You may already have a sense that the statement to be proved is true, but to make sure your intuition is correct and to develop a careful proof, rewrite the statement using names such as a and b for the odd and even integers, so that you will have a convenient way to refer to them. For all integers a and b, if a is odd and b is even, then a minus b is odd, or different variations of that. So the starting point should be something like, suppose a is an odd integer, any odd integer, and b is any even integer. And the conclusion to be shown would be, we must show that a minus b is odd. If, in addition, you know that how to use the definitions of odd and even, you will have reduced the creative part of developing the proof to a small but crucial section in the middle. Which leads to Theorem 421. The difference of any odd integer and any even integer is, in fact, odd. Identify a mistake. Well, if n is any even integer, then minus 1 to the n equals 1. And it gives a proof step by step. If n is even, then it equals 2a, which means minus 1 to the n equals minus 1 to the 2a, and that equals minus 1 to the a to the second, which equals 1. Well, sounds like it's jumping to a conclusion. Yeah. Incorrectly jumps to a conclusion in line 5. Although it is true that the square of any non-zero real number is positive, it does not follow that the square of a minus 1 to the a is 1. Exercise 10 at the end of the section asks you to give a correct proof of this theorem. Solving an existential statement, or showing that an existential statement is false. Well, we know that the negation of an existential statement is universal. It follows that to prove an existential statement is false, you must prove that prove a universal statement, its negation, is true. Show that the following statement is false. There is a positive integer n such that n squared plus 3n plus 2 is prime. Now, proving that the given statement is false is equivalent to proving its negation is true. The negation is, for all positive integers n, if n squared plus 3n plus 2 is not prime. Because the negation is universal, it is proved by generalizing from the generic particular. Claim: there is a positive integer n such that n squared plus 3n plus 2 is prime, is false. Proof: suppose that n is any particular positive integer. Factoring that shows n plus 1 times n squared plus 3n plus 2 equals n plus 1 times n plus 2. In addition, n plus 1 and n plus 2 are integers because they are a sum of integers, and both n plus 1 and n plus 2 are greater than 1 because n is greater than or equal to 1. Thus, n squared plus 3n plus 2 is a product of two integers, each greater than 1. So, n squared plus 3n plus 2 is not prime. And that will be it for that new section. And then we can go to section 3. Is it going to behave? Elementary number theory and methods of proof. Section 3, rational numbers. A real number is rational if and only if it can be expressed as a quotient of two integers with a non-zero denominator. A real number is not rational, is irrational. More formally, if R is a real number, then R is rational if there exist integers a and b such that r equals a over b and b does not equal 0. So, is 10 over 3 a rational number? What about minus 5 over 39? 0.281? 7? 0? Yes. 0 over 2. How about 2 over 0? No, it's not a real number. And the denominator is 0. Is 2 over 0 a irrational number? No, it has to be a real number to be irrational. 2 over 0 is not a real number. So is 1, 2, 1, 2, 1, 2 on to infinity a rational number? We'll look at that one in a minute. And if m and n are integers and neither m or n is 0, then m plus n over m times n is a rational number? M and n are integers, so yeah, it's a rational number because the m plus n is an integer and m times n is an integer, and neither m nor n is 0, so the denominator is not equal to 0. So we went through all these, and no, n is not 2 over 0 is not a real number. No, because every irrational number is a real number, and 2 over 0 is not a real number. The way of looking at this is x equals 12 over 99, so 1, 2, 1, 2, 1, 2 on to infinity is in fact a rational number. And since m and n are integers, also m and n, m times n is not equal to 0 by the zero product property, which states if neither of two real numbers is 0, then their product is also not 0. More generalizing from the generic particular. Most problems are stated in informal language, but solving them often requires translating them into more formal terms. Theorem 431, every integer is a rational number. Proving properties of rational numbers. Prove that the sum of any two rational numbers is rational. Say m, m equals a over b, n equals c over d, m plus n equals a b plus c over d, and then that would be equal to dA over BD plus CB over BD, which equals dA plus CB over BD. And the numerator and denominator are all integers. And it also stated that, B and D not equal to 0. And the zero product property it would say that the denominator is not 0. So the sum of two rational numbers is rational. Did I do my algebra right? Did I do my algebra right, or did I screw up somewhere? Okay. It's been a long time since Algebra 1. A good 40 years. So I don't claim to be a master at this stuff. But yeah, and they go through it. Formal restatement. Where am I starting from? What am I supposing? Then to show R plus S is rational. I'd used M and N, but whatever. Let's see here, and then they go through substitution, fraction with common denominator, fractions with adding fractions, zero property law, product property here, and we get to theorem 432. The sum of any two rational numbers is rational. So, deriving new mathematics from old. So, suppose that you already proved the following properties of even and odd numbers, odd integers. The sum, product, and difference of any two even number integers is even. The sum and difference of any two odd integers is even. The product of any two odd integers is odd. The product of any even integer and any odd integer is even. The sum of any odd integer and any even integer is odd. The difference of any odd integer and minus any even integer is odd. The difference of any even integer minus any odd integer is odd. Use these properties listed above to prove that if A is any even integer and B is any odd integer, then A squared plus B squared plus 1 over 2 is, in fact, an integer. Well, you suppose that A is any even integer and B is any odd integer. By property 3, B is odd, B squared is odd. And property 1, A squared is even. Then by property 5, A squared plus B squared is odd because 1 is also odd. Oh, and because 1 is also odd, the sum A squared plus B squared plus 1 equals is even by property 2. Hence, by definition of even, there exists an integer k such that A squared plus B squared plus 1 equals 2k. Dividing both sides by 2 gives A squared plus B squared plus 1 equals k, or all over 2 equals k, which is an integer. Thus, A squared plus B squared plus 1 is an integer if A is even and B is odd. Derive the following as a corollary of theorem 432. The double of any rational number is rational. Well, The double of a number is just its sum with itself. Since the sum of any two rational numbers is rational, theorem 432, the sum of a rational number with itself is rational. Hence, the double of a rational number is rational. Formal version of the argument. Suppose r is any rational number, then 2r plus equals r plus s, or r plus r, is the sum of two rational numbers. So by theorem 432, 2r is rational. And that will wrap it up for section 3. So we are moving along, and we can call it a day at this point. The midterm will be next Thursday. It will be chapter 4 definitely might include some other stuff from the previous chapters. But grades are due in the registrar's office Monday the 9th at 5 p.m. So at some point before that, your grades will be visible on Canvas and on pause. So there you go. But anyway, have a good day. See you on Thursday.